Good evening for me because I'm from New York. My name is Caroline Mondaka. I am a science teacher at Martin Van Buren High School in Queens Village. I just wanted to start off by telling you a little bit about myself. This is my 17th year of teaching, but I didn't start my career out in teaching. I was actually an acquisitions editor in a medical publishing company. I ran the pathology and the oncology program. One day I was riding the New York City subway and I look up and I see an ad and it said, "Do you remember your third grade teacher's name? Who will remember yours?" So I get to the office, I call my husband and I say, "I'm leaving publishing completely. I'm going to become a teacher." And he said, "Okay, sure." Fast forward, after teaching for many, many years, about 13th or 14th year, it was the best decision I made, by the way. I started feeling burnout at about 13, 14 years. And then I applied for a fellowship to go to Little Cayman to study the climate change in the coral reefs. And this was intended for educators. And I realized while I was in Little Cayman that this reignited my passion for research, but more importantly, it reminded me of the urgency to teach our students about the human impact on climate and what's going on in terms of the coral reefs and the environment. And so, like Matt said, this is my third year with CCRI and my third year with the team. The previous unit plan that I created my first year also passed SMD product review. And that's when you download the presentation, the link is there. I want to tell you a little bit about my school because I think that it's significant. A lot of people think NASA unit plan, it's out of my reach. I can't implement this in my classroom. So my school is considered a underprivileged, challenged, hard to staff school. The students are underrepresented. We are 1,200 students strong. We have over 80 teachers. 2/3 of my students are either on free lunch or reduced lunch. You'll see that 15% are below federal poverty level. That 9% of students who are in shelters or temporary housing, that's skyrocketed to about 15% after COVID. 12% of my students have learning disabilities or are emotionally disabled, and 13% are ESL students. They're new to the country. About 2/3 of our population is Black and Hispanic, and the Asian population, that 29%, that's actually comprised about the majority of our Ls. They come from India, Bangladesh, Pakistan, and 3% are white. I just wanted to mention that last year, and any educator can apply for this. Last year, we applied for NASA's Education Downlink. Again, the link is going to be provided to you, where my students were able to Skype live with astronaut Jessica Meir while she was on the International Space Station. The reason why I'm mentioning this is because it was life-changing. It embedded our school in NASA resources, and there were more than 600 students in the audience, and you could hear a pin drop. That's how captivated they were. So we had more than 600 students, 900 additional viewers who logged in via NASA TV. My favorite story of this is one of the students came to me and said, "Ms. Wang, my uncle and aunt watched from Bangladesh. They streamed it live while it was happening in our auditorium." So Matt already mentioned a little bit about what CCRI is. So I wanted to mention it again. It is a year-long STEM engagement opportunity for educators like me who teach science. And we work directly with grad students, with a grad student, and we're led by our mentor, a NASA scientist. And we have a research project that we work on. Not only are we considered associate researchers and we're really immersed in the research, but our role is to really bring that research back and implement it into our classroom to give our students that authentic experience of being involved in real research, and also to be able to reach out to our communities and let them know exactly what we're doing. That NASA downlink, that education downlink, was one of the ways that my school did that, is to bring the community together and show them what we were doing. So this is a team that I helped lead last year. You'll see on the far right, that's Dr. Dorothy Petit. She's from Lamont. She's an amazing woman. And to her left, that's Molly Dunton. She's since graduated Columbia, but last year she was a grad student at Columbia. And there I am on her left. On the left-hand picture, on the far left, that's Grant. He's an undergraduate student. And in the middle right there is Saeed. He's a high school student. He happens to be my high school student. He's actually since graduated, and he's now at Cooper Union in New York. This vertical structure is amazing to me because Not only are we being mentored by Dorothy by Dr. Petit, but my high school student was applying to colleges. And not only did the grad student and the undergrad student really help guide him in educational, but also personal things. And for me, without them, without the entire team, my unit plan would definitely not have come to fruition. It was truly a labor of love. So our study was on salt marshes, and you might ask why salt marshes. So salt marshes are essential for coastal protection, storm surges. They're naturally there for water filtration. They're a source for biodiversity. You'll see in the presentation that carbon sequestration is one of our focuses. However, like many of Earth's other natural resources, many of them are threatened by things like upstream pollution, drainage for agriculture, human development, tourism, of course, sea level rise, and sediment loss, which are huge. The way we approach this is called the paleoecological investigation method. And what we do is we go back in time to study what happens in the past so that we can better understand how the wetland ecosystems, the salt marshes, are going to respond to future climate change, future sea level rise, urban sprawl or expansion, and that way we can better manage these systems. We can also determine how much carbon that they're going to sequester. So some of the terms that you're going to hear me mention are marsh core. Essentially, this is a vertical sequence where we're getting a snapshot of soil, and it's a vertical sequence. It maintains the stratigraphic layers of sediment, and it preserves the depositional sequence. So you can see what's happening present day compared to 10 years ago, compared to 20 years ago, and so on and so forth. Blue carbon is the focus of my unit plan. And blue carbon is essentially the carbon that's stored in marine and coastal ecosystems. Coastal ecosystems such as mangrove forests, seagrass meadows, or salt marshes. This area of study has become very popular, I'd say in the last 5 or 7 years or so. What people don't realize is that the carbon is stored in the sediment, it's stored in the soil, in the salt marshes. As sea level rises and washes away the sediment, it prevents these salt marshes from being able to store carbon. But it's doubly bad because what happens is that carbon gets released into the atmosphere as carbon dioxide. Foraminifera, we study as well. These are single-celled organisms. They have shells. They are very sensitive, very specific to pH, marsh elevation, and sea levels. So very specific species will exist in very specific conditions. Plant macrofossils, these are preserved organic remains of plants. You can see them without a microscope, but we use a dissection microscope. And that gives us an idea of at what point certain plants existed. So whether it was high marsh plants or low marsh plants, for example. And you'll hear a lot about LOI. LOI represents loss on ignition. What we do is we sample this core. We literally ignite it, we burn it, we bake it. And then the percentage that's lost gives us the organic content of that. And that tells us how much carbon there's going to be in it versus sand or silt won't burn off, and that will be what remains. Okay, so part of our research study, which is what this unit plan is based on, is how can we generate blue carbon stock and loss estimates due to anthropogenic impacts and climate change. Historically, studies have looked at salt marshes or wetland ecosystems and said, okay, this is how much carbon is stored based on 1 meter in depth. We have found that salt marshes range more like 6 to 10 meters in depth, the ones that we measured. So it's been grossly underestimated. So once again, the blue carbon refers to the carbon that's stored in these marine and coastal ecosystems, whether it's salt marshes, mangroves, or seagrass meadows. And what we did is we looked at the historic carbon storage from the 1880s and compared it to present day. We used a combination of satellite imagery to look at what the maps looked like back then, a combination of probing where we go to the marshes and we probe for depth to see how deep the marshes go, literally manually just seeing how deep these marshes are, and then coming back with samples of the core to calculate loss on ignition and seeing how much of each level of that core contains carbon content. And then we looked at the impacts of human development on marsh carbon storage potential. So just to give you an idea, this was our poster that we submitted to AGU. The reason why I'm showing you this is to show you the maps that we did and the calculations that we did. And I have something that's a little bit more up close for us to look at so you can understand the background of the unit plan. This was my presentation at AGU. And if you're taking a look at it, we provide the background information in the unit plan, but part of what I think makes this unit plan stand apart from others is that I really wanted to provide authentic STEM experiences. So I'm showing you a picture of us out in the fields, but on the right-hand side where it says field work and lab work, I've built in where students are mimicking what we did out in the field by also going out into the field and measuring temperature as well, as part of the urban heat island effect. And on the right, you'll see I used ArcGIS, which may sound foreign right now, but it's satellite imaging. It's a NASA resource, and they do amazing things in providing educators with a whole suite of resources that students can actually map location and map past wetlands, present wetlands. They can map about almost anything, and I'll show that to you in a second. Okay, so how did we go about gathering all of this material? So in the field, we would get the sediment core, which I'll show you a picture of. We probed transects, so that's measuring how deep that wetland is. We looked at flora, we picked foramifera, we got these samples. In the lab, we would perform the loss on ignition. That's the burning of the core to see how much is organic. X-ray fluorescence pretty much gives us the elemental composition. So in the past, you see there's like no lead, for example, and then you see once humans come into an area, lead starts to increase, copper starts to increase because of copper mining, and then you start seeing the trends of when the Clean Air, Clean Water Act comes in, lead starts to come down. So that's an example. We looked at isotope analysis. We looked specifically at nitrogen and carbon. Nitrogen specifically because of human waste and fertilizer has tons of nitrogen in it. So you could see the spikes that correlate with human impact. Macrofossils, I mentioned before, that's plant matter that you can see, pollen from plants, as well as foramifera. We abbreviate that as forams. So this is what it looks like. And these slides are actually included in the unit plan so students can see what they would be doing. So on the left, that's us probing at Jamaica Bay in New York. That's a wetland close to my school. And those are actually very inexpensive chimney sweeper extensions where you can go to any hardware store, a larger hardware store, and you buy them and they actually attach. So each rod is like a little over a meter long. And as you're going down, you keep attaching them and you keep going further and further down. I think the deepest marsh we did was about 10 meters deep. So that's huge. It's really deep compared to historically what's been estimated as 1 meter. 10 meters is 10 times, and you can imagine that volume of carbon. On the right-hand side is what the core looks like. So it's a Russian core. You twist, you go down. It doesn't compact the soil. And then when you pull it up, and then handy dandy materials like aluminum foil and plastic wrap, we wrap it up and it goes into a repository or into a fridge. And this is us coming back. So we're sampling every 2 to 4 centimeters, and essentially those crucibles are holding parts of that soil, and they get dried and they get ignited at 550 degrees, and that way all the organic material is burnt off. So this is actually in my previous unit plan, and if you have a powerfully enough oven, you can actually do this in the lab, in your school lab, and be able to do the calculations. So this is where we stood with our research from last year. What we did was we took the average loss on ignition, that's the average organic material, and we multiplied that by the average bulk density. So bulk density is an indicator of soil compaction. So if it's rich in organic matter, it usually has a lower bulk density, whereas inorganic material like sand, silt, and clay are going to have higher bulk densities. You multiply that by the area of the marsh. So the area of the marsh we got from ArcGIS or from satellite imagery. You can even use Google Earth, to be honest with you. And then from probing, being out in the field, you find the depth of the marsh. So with the area and the depth, you've already got volume. And then we multiply that by 0.5. That reason that 0.5 is because roughly half of the organic matter is comprised of carbon. But we wanted to represent this in a way that the public would be able to understand, that kids also would be able to relate to. So we called it a carbon equivalent. How many cars annually are we actually thinking about? So we took the total carbon storage of the marsh and we divided it by the average carbon emitted per car. And that's how we came up with our calculations. So these are the marshes we looked at. This is along the Hudson Estuary. So some of the marshes are Ragged Rock, Plum Bank, Quinnipiac, Nels Island, Great Meadows. We've also looked at marshes closer to New York, for example. I just wanted to show you one example of one marsh that we looked at so you can better understand the basis of this unit plan. And this is Plum Bank. So we were there. We took pictures. These are my pictures. And I wanted to show you the loss on ignition graph. So if you follow me here, if you're looking on the y-axis, 0 is the top of the core. That's depth. So 0 means present day. And as you go deeper down, those are centimeters. That's the depth. So 100 centimeters is approximately 400 years. That's how far back we're going. Okay, on the x-axis on the bottom, that's percentage of organic material, and on the top axis, that's the weight. So if you follow just the blue line, and if you go from 200 centimeters deep, and you come up and you follow it up with me, you'll see that it looks like organic material is dropping off and the organic material increases. And if you look around 44 centimeters, it's like, oh, wow, there's a drop in organic material. Did they cut down the trees? That's actually not the case. If you look at the bars now, the white bar graphs represent the amount of inorganic material and the pink represents the organic material. The organic material actually stays pretty consistent. However, you're seeing an influx of inorganic material. That influx of inorganic material, we are correlating with human settlement. And we see this across many of the cores, that it's about 40, 48 centimeters, 54 centimeters. And lo and behold, at Plum Bank, there are actually houses that were built surrounding that area around that time. Okay, so this is what a transect looks like. So you can use ArcGIS for this. You can use Google Earth for this with your kids if you wanted them to map something, for example. So these are 12 probe measurements. So we started on the far right-hand side. We just drove up to it with our galoshes and we walked in. In the middle, you'll see like a stream, or it was actually like a river. I think one of our boots is in there because one of us started sinking in there. So our boot's still in there. We had to come out, ran to a store, bought new shoes, and then we drove around to the other side and then walked in and probed further. So if you look at the average depth, minimum was 1.24 meters. Maximum was 6.2 meters. Historically, if scientists are estimating, previous papers are estimating 1 meter in depth, they're grossly underestimating how much carbon can be stored in this wetland, for example, in this salt marsh. So we came back and we mapped it out. So in the 1880s, that's the top graph, you'll see 1.6 square meters of land. Then in the 1990s, it dropped down to 1.3 million square meters. And what we calculated was, this is the loss. Historically, it was storing about 325 million kilograms of carbon, and then it dropped down to almost 280. That's a negative 14% loss. We equated that because what's negative 14% when a student is looking at it or when the public is looking at it? But we compared that to cars equivalent, and it's 36,000 cars that we're talking about. That's how much carbon now is no longer being stored, no longer being able to store that carbon in that salt marsh. So this is what our data suggests. Blue carbon stocks, routinely underestimated. Human development has negatively impacted wetland health and subsequently decreased blue carbon storage. So as coastal wetlands are degraded or destroyed, whether they're being filled in or drained, a variable portion of that stored blue carbon is disturbed. It's emitted into the atmosphere as carbon dioxide, but it also decreases the ability for that salt marsh to continue storing that carbon. Okay, so the whole point of all of this research was now to bring it back into the classroom. And I knew that there were certain things I definitely wanted to do. I wanted to make use of NASA's carbon monitoring system. It's a great website, great resources. I wanted hands-on activities for the students. I wanted them to use infrared temperature guns to measure varying temperatures right by my school. We're in an urban area and right by two local salt marshes. So our salt marshes are actually surrounded by urban areas, by two highways. And this, from what we've seen, happens quite often, that if you go to a salt marsh, people love living in that area because it's so beautiful to look at, that condo complexes come up, buildings come up. And so it's a great way to see the differences in temperatures. I wanted to also be able to use computational skills, trick my students to do math, essentially, and to utilize NASA's imaging resources. As soon as I ordered ArcGIS, people were like, oh, that's a NASA resource. No way. These students are not going to be able to handle that. They handled it and they went beyond. I also wanted students to be out in the field. I think that there's nothing more exciting than a student getting dirty and being out in nature. We tell them to save the environment. We tell them to save these wetlands, but most of my students have no idea what they're saving because they've never gone and left their neighborhood or definitely not gone to a salt marsh. So with these chimney sweepers, we wanted to take them to Alley Pond and be able to measure depth and calculate carbon content. Given COVID happened, I wanted an alternative capstone where students didn't have to be out in the field, and even though they were inside their homes, that they could still do a global tour, essentially, of what wetlands exist all over the world. And that's when I thought about having the ArcGIS Blue Carbon Story Map. Okay, so the first lesson introduces students to wetlands, human impact, climate change, and sea level rise. So I wanted to show you the first video. It's just to give you an example of what kind of resources are in it. The first video is on the carbon cycle.
Pine trees, bumblebees, and Swiss cheese, what do these all have in common? It's carbon. Carbon can be found almost everywhere. Find out just how important carbon is to life on Earth next on Real World. Carbon is not only the fourth most abundant element in the universe, it's also one of the essential building blocks of life. It's in our bodies and in our food. But what is carbon anyway?
Carbon is one of the basic building blocks of life on Earth. It's found all over the place, like in animals, plants, and it's also found in non-living material, like rocks and the atmosphere.
Carbon is important for many reasons, including providing lots of the power that we use. It's found in coal, it's found in fossil fuels, it's found really in all of our main sources of energy. We can find carbon in many different types of source pools. There's a lot of carbon in the ocean. That's actually one of our main carbon pools on our planet. You can find carbon in the atmosphere as different gases, such as carbon dioxide. And you find lots of carbon in the terrestrial areas, so in plants, in trees, or in soils.
So what else do we know about this carbon cycle?
So the carbon cycle is the cycle of where carbon goes and also how carbon moves from one pool into a different one.
Carbon cycle is a system, this Earth process, that transfers carbon from the plant material to the atmosphere, back to the plant material, from the oceans to the atmosphere, back to the oceans, and from far below ground, from fossilized carbon pools to the atmosphere.
So fast-moving carbon, for example, is what gets stored in plants. You have photosynthesis that happens, which is essentially really a mechanism by which plants are able to absorb carbon from the atmosphere, and they essentially use the carbon to make sugar, which is the basis of all carbohydrates. And that carbon that's fixed there in these plants is fast carbon.
Slower carbon will refer to, over time, sort of the integration of perhaps atmospheric carbon into the ocean and down into the depths of the ocean. One manner in which it's transferred from the atmosphere to the oceans might be through the photosynthesis that's done by plankton in the ocean, and then the consumption of that plankton by higher level species, and then the eventual decay of some of that organic material. Those species will, to some extent, decay and be transferred to the bottom of the ocean, where the carbon that used to be part of those species gets locked away in ocean sediments.
Humans have a huge impact on the carbon cycle because essentially we are changing how it is. We're taking a lot of these pools of slow carbon and burning it and putting it into the atmosphere. So we're really changing where the carbon is, and that has some big implications. So we're not really changing how much carbon is there. The amount of carbon is always the same, but what we're changing is where it is and what form it's in. So if you put the carbon, take the slow carbon, you burn it, and you put it into the atmosphere, it gets expanded, and the atmosphere is a much smaller pool than the ocean is, for example, or our terrestrial reservoirs are.
Humans have a really important role in the carbon cycle. But how does NASA measure carbon as it moves?
We have different ways of measuring carbon. For example, we work on measuring the carbon that's stored in trees. And to do that, we use different types of instruments. We do field work, and we also use satellite data. For example, data from some new satellites like ICET-2 and JEDI.
One way we do those measurements is with satellite imagery or satellite estimates. We use LiDAR instruments that are in space that are pointed down at the Earth, that shoot LiDAR pulses towards the Earth and measure the time that it takes for those pulses to return to the satellite sensor. From those pieces of information, we can learn about the height of forests and other structural characteristics of the forest canopies.
In addition to using the satellite data, we also have to do field work. We go in the field and we measure what species it is. We get the biometry of a tree, which is a biometry is measuring of the living things. We take a tape and we put it around the tree and we measure the circumference, measure the height of a tree, and then we compare that to what we're getting from the satellite.
We would like to get a better understanding of where carbon exists on the landscape.
Carbon really is essential to all life as we know it. And we can see the carbon cycle in motion thanks to NASA's Eyes in the Sky, on the ground, and in space. See you next time on Real World.
So this is just an example of one of NASA's eclipses. These videos are 3 to 5 minutes. They're fantastic. I also wanted to give you a brief tour on NASA's Carbon Monitoring System website. So it's the link is going to be in the notes. And if this is sort of a video, it's a screencast so that I can walk you through it. This is NASA's Carbon Monitoring System. And each of the icons on top, if you click on them, it actually gives you an idea of what these definitions are, whether it's land to ocean to atmosphere influx, for example. And as they're clicking on each of these icons, they can see what they mean. So decision support, ocean biomass, global surface, land biomass. So they get the vocabulary review there. Part of the lesson is for them to create a poster, their own poster. And so here are a gazillion examples of posters. And the reason why I did this is because in a poster, they have to use images and very little text, which means that when they're representing it and they're presenting it, they have to know their stuff in order to present it. And so here are some examples where it's all images, very, very little text, and they have to be able to select the graphs that they want to talk about or the images that they want to talk about or the visualizations and be able to represent it. So this is one of my favorite sites. It's a plethora of information and then hyperlinks to other areas as well. So that was just a brief tour. So this one is also a really great one, and this is the Blue Carbon Initiative. This site is actually in collaboration with NASA. I love this site because it's a really quick overview for the kids. It also, the presentation of it is very similar to a story map, which is going to come up towards the end. So again, this is a screencasting of the website. So once it plays, I think it's loading a little bit, you'll be able to see it. So as you scroll down, it tells you all of this data, what the International Blue Carbon Initiative is. And this is what I mean by it takes the format of a story map, where the image stays and the text keeps moving, and it gives you all of this great data. It maps it out for you where the wetlands are. It tells you what mangroves are, what tidal marshes are, what seagrasses, and why they're important. So it gives you a really great overview of what the Carbon Initiative is and what's being done. So this is more like an introduction to blue carbon for the students than anything else. But there are other NASA resources as well that are used throughout the unit plan. And that's coming up in the next slide. Okay, here we go. So things like the carbon cycle and ecosystems, globalchange.gov. So these are all collaborations. If you look at all the icons, for example, NASA's biological diversity and ecological forecasting. So the students are able to access all of these representations and be able to create a poster with really solid information, but being able to use a lot of the graphics. And speaking of graphics, JPL actually has an infographic where you can build a poster, essentially. You can download text, download images rather, and it's a wealth of information there, and it's free access. So it's a fantastic resource. And I wanted to bring this unit plan up to current events. So it's been in the news quite a bit, our Moon to Mars NASA mission. And I wanted the students to be able to connect astrobiology questions about the potential for life on Mars. Why are we going there with the high school curriculum? And interestingly enough, Perseverance, the rover, is going to search for signs of ancient microbial life by drilling and collecting core samples. So those core samples are much smaller than the core samples that we've collected, but it's the same concept, the same notion. If you remember from the e-clip that we just showed you, you'll notice that the GLOBE program flashed up. So GLOBE is, to me, one of my favorite sites where the students are collecting data. They're ground truthing and comparing it to NASA satellite imagery, for example. And then they get to upload their information into a database that's shared. And it's cool because if you get trained, you can actually pop up on the GLOBE map. It'll ask like what schools are participating in the GLOBE program. And so here's a quick video of the screencast of just walking you through quickly through GLOBE. Super friendly, super easy to use. This is the GLOBE program. So as you go, you see that there's different campaigns that are happening. So the GLOBE data, for example, you can get data, you can visualize data. My favorite is the Do GLOBE. They have measurement campaigns, and one of them is the urban heat island. So if you scroll down once you're there, the urban heat island campaign is essentially the students are going out and measuring temperature. This video I'll show you in a second as well. And you can get trained virtually as well. In fact, I actually use some of the slides that they use as part of their training. So they teach you what infrared guns you're allowed to use, how to measure distance from the surface that you're supposed to measure, how frequently you're supposed to measure, when the satellites come over so that you can ground truth. And with each of these modules, you click on it, and it's almost a self-paced training. They also offer live classes. With COVID right now, that's probably suspended, but it's an excellent resource. And I download those modules and I use some of those PowerPoint presentations with my students as well. Okay, then this group of students they're my students, and they're not necessarily out in the field yet. They're not out in the salt marsh, but they are out in front of my building. So this is where they start. They make a map of where our building is. They have to figure out where do they think. So they're creating hypotheses and predictions. Where is it going to be hotter? Where is it going to be cooler? Does vegetation affect it? Does the color of the surface affect anything? Metal versus concrete, impervious surfaces. And I just wanted to show you a urban heat island video that comes out of NASA. This is a really fantastic resource as well.
urban heat islands affect human health and it affects energy consumption. Those two things alone are enough to drive worldwide interest.
When we build an urban area, we're replacing the vegetated surface and also the soil surface with this impervious surface like the paving material and the building material. By doing this, we're basically warming the urban areas, and this will generate a temperature difference, and that's what we call the urban heat island. We find out that the urban heat island affected by several factors. The first factor will be the surrounding ecological context. And then will be the size of the city. When talking about size, we mean both the area of the city and also the population size of the city. And then will be the shape of the city and also the development patterns of the city.
We used a variety of satellite data, both land surface temperature data from MODIS and also impervious surface data from the Landsat satellite. Impervious surface data essentially tells us how much building material is on the land surface in order to study the urban heat island. The urban heat island is much larger if you convert a forested area into an urban area. And this is because the urban heat island is a relative measure. So urban areas and forests are much warmer than the surrounding landscape than they are in deserts, for example, because the surrounding landscape is already warm. I think the general public should be interested in urban heat islands because of the fact that it's where most of the people live, and in the next 50 years, we're going to see 80% of the global population living in cities. And the urban heat island matters for everything from health, like asthma and heart conditions, to how much heating and air conditioning you need to use to cool or heat your living space.
So that was one of the shorter NASA Eclipse, but I feel like it really got to the point of urban heat island act. Okay, so just switching gears a little bit, I wanted to have students, like I said, bring in math. And so using Google Earth Pro, because all the students know Google Maps and they understand this platform really, really well. Essentially what you're doing is you can pull up a map from the past. I think this one was on the left, 1990s, for example, of Jamaica Bay in New York. And they literally draw a polygon around it, and that will tell them area. And then they come to present day, and then they measure it, and they can calculate the loss. And one of the reasons why I started with this is you start with an easier platform, and then you advance to ArcGIS. ArcGIS is an imaging. It's a satellite imaging platform, and so it's a mapping function. So you can pull the national wetlands inventory for anywhere in the United States, other countries as well. And so you can take a look. So on the left is Jamaica Bay. On the right is wetlands in Connecticut, for example. And the purple is current day, and then all of that loss is shown in the green. So the students can see the marshes in their own neighborhood, or they could see it on a global scale, and they're utilizing a NASA resource, and they don't realize it. The platform is very similar in how they use it. So if you sneak in Google Earth Pro first, and then you go into ArcGIS, they don't realize that they're actually using a very advanced technique. So part of my capstone, so it's a two-part capstone, two versions. One was going out into the field and probing in the marshes so they could probe for depth and then come back and calculate how much volume there is and calculate how much storage potential there is. The alternative capstone is, if you are completely virtual, or you can use this in addition, is creating an ArcGIS blue carbon story map. In terms of the probing, what I did was I created a development of the lab protocols, but the students take the initiative to do it. So here you're giving them instructions. They have to develop the materials and methods from scratch. They have to be mindful of budget. They have to be mindful of safety, where we're going to go. This is when mapping comes in. So they have to map that area that they want to go to. So they have to make sure that they're looking at rivers and streams and being very cautious about that when it comes to safety. So this is part of the plan. After the materials and the methods, mapping has to come into it. And then the data that they're going to collect. So what's going to affect how wet it is outside? Did it just rain? Is it cloudy? Is it sunny? How far away are they from urban areas, for example? And then observations that they're going to make. And then finally, potential challenges. And so you'll notice that there's a draft format and then there's a revision format. So that way they can constantly get feedback and they can keep revising it. And then as a class, they would come up with a group protocol on how to do it. In terms of the next part, actually, I didn't want to flip to that yet. In terms of the next part, I wanted to show you a little the ArcGIS tour. It's a little video of what it looks like in terms of creating a blue carbon story map. This is the alternative. So I created this relatively quickly. Essentially what it is, you log into ArcGIS. So you can create accounts for all your students. You're watching what they're doing. So they won't publish outside of your organization. So you see what they're publishing. So if you're publishing within your school, that's all you see. I love these little subheadings. It helps the kids break things down. This is called a sidecar, where as you're, the next part, as you're moving the text, your image stays. So they're reading the text, they're still seeing the image or the transition in images. I love this feature where you can compare past to present. So here it's an example of land subsidence. So the land is sinking and sea level is rising. So you see less of the marsh. And this is all built into the ArcGIS story map. This is called a map tour where you're going from one area of the map to the other. And so these are just images that I put in from my research. So this is where the diversity part of it comes from. I'm Taiwanese. My parents are from Taiwan. My husband is Chilean. And so I used myself as an example and I showed the kids, look, there's wetlands everywhere, all over the world. It does two things. One, shows you that wetlands are all over the world. It unifies us, but also it diversifies us because the students get to celebrate who they are. So you'll notice I included NASA resources, and this is one of my favorite. And so when you embed it into the story map, people can actually click on it and it hyperlinks you directly to where the source is. So they're looking at satellite images and all of this. And then what I wanted to show you was an example of my students' work. Just waiting for this video to end.
Hi guys, this is our story map, Blue Carbon, a trip around South Asia, and it was
Oh, we can continue playing that, Barbie. That actually works out well.
made by my partner Shazia and me, Steffi. So our first heading, as you can see in like the navigation things on top, which is the gray section, is blue carbon, and the subheading that we did is what is blue carbon. And to actually balance it from text to images, we embedded a YouTube link so people could click on that if they needed further information. And underneath, we included an image just in case if people were like visual learners and they needed to see that. The next one is what are blue carbon ecosystems, and we inserted a picture of the actual biodiversity so people could actually see what it looks like. The next one was wetlands, which is our next heading, and underneath we embedded a NASA article that we looked at while researching these wetlands. We researched 3 wetlands and we had 3 different NASA links that we used. And for this, we used a sidecar with the docked panels so people would be able to see what the actual wetland looks like while reading the information provided. We have another NASA link down there as well. And this is the first map that we created on ArcGIS. This shows the global distribution of CO2 emissions, and we put it as like a larger images so people could actually scroll through it and look around the world. That is another NASA article that we used on their blue carbon mapping initiative. For this subtitle, we used the gallery feature, which allows us to place multiple pictures next to each other so people would get more of an idea, so you wouldn't have to stack the images. That is another NASA website that we embedded while doing research. For the human impact on the wetlands, we included a video so it would balance nicely with the amount of text that we have, and it's also further information. For that one, we use the bullet feature, so it would be more organized, and we did the same thing here, so it wouldn't be a huge paragraph. For the wetlands in India, this is the other sidecar that we used, and it's a docked panel which shows us what the actual wetland looks like with the information that we have. And this is our map on the human impacts on this wetland. This is also a sidecar that we used, so people would actually be able to go to the map themselves. As mentioned previously, this is the same gallery image that we use, except this is with just 2 pictures at the same time next to each other. This is what they look like. If you click on them, they get bigger. This is the quote feature that we used, so it would actually look like a quote rather than a massive paragraph.
So for the trip around South Asia, we used the guided tour map, and what's really great about this is that you can actually go through places on a map. So the great thing about this is that you can pick the locations on the side, so you don't necessarily have to go in order. You can go with anyone you choose to, and even if you start from the middle, you can continue to scroll down and it will take you right into the next place. So having the image at the top really helps because you get an insight on what this place actually looks like, and then you see the map itself will move and show you the location of wherever we're talking about. We use the heading at the top, so it's just bold and you can see the difference in the places. And then we space out the text, so once again, it's not just like one large paragraph. But the great thing about this is that you can see the location on the map and also view the text and facts on the sides. So that was really helpful. So one of the reasons that we picked the wetlands that we picked was because of the fact that these countries aren't as developed. So India is a common background for me and Steffi, heritage-wise. And the other places that we picked around South Asia, these countries are not as big and developed as the US, the UK, and China. So one really great thing about looking at them is we have further insight on how destruction to wetlands affects these places, whether it's agriculture or the fishing economy, or even to then just the daily lives of the people who, use these rivers and these places for religious purposes. And even to then, in the initiatives, the first one was talking about the effects of religious practices on these wetlands, like the amount of flowers that get dumped into these rivers and these waterways that are covered in pesticides and chemicals. So it was really interesting.
Okay. Sorry, I had to cut her off because it was a very long video. And one of the last slides that I just wanted to show you that kind of alluded to was this represents just one of my classes. So if you look at the diversity of it, we're looking at Spain, we're looking at Bangladesh, India, Japan, Guyana, Trinidad, Tobago, Brazil, China, Yemen, and Pakistan. One of my favorite subtitles was one of the students wrote, "There are many stories on blue carbon, but this story belongs to me. The story is mine." So just to give you an idea, when you have that aha moment as a teacher and you're like, wow, this really worked. This for me really, really worked. And I just wanted to thank everyone